Okay, yeah. So I think we can start now. It's already 1:15. So in today's lecture, as I mentioned in the previous lecture, that we will be discussing more about algorithm analysis and particularly with a focus on time complexity. And this time complexity is also the part of assignment 3, I guess. So where you have a task, for those tasks you need to provide the time complexity estimate for a few of your methods. So today's lecture is also important from that point of view. And here, as it says, that we will start with some introduction about algorithms and how you can write down and what the algorithms are, and what is the use of the different algorithms. And then we will move forward to the time complexity. So beginning with, can someone describe, I guess being a student of computer science, all of you will have some information about an algorithm. So what an algorithm is? Anyone? Yep. Set of instructions. Yeah, in a sequence. Yes. Set of instructions for what? To solve a problem. Yeah. So it's yeah. Simply we can say that yeah, an algorithm is a set of instructions or a step-by-step set of instructions. But what's important is the instructions are meant to solve some problem. So if you have a problem and you want to solve your problem, so usually, I mean, you don't solve your problem in a one step. You usually have multiple steps where you address the problem in a smaller steps, and you go, yeah, you begin with the step 1, and then you move on and solve parts of the problems, and once those parts are solved, then you go. So simply defined as it says that it's an unambiguous description, and that's also very important, that your algorithm should be, yeah, very precise, and it should not have like double meanings or ambiguity in it, because otherwise if it's not unambiguous, different people may come up with a different implementation for the same algorithm. And there are some historical facts. The history of algorithm is quite yeah, old. The first algorithm was this greatest common divisor. It came around 300 BC by this Euclid, the mathematician Euclid. So that's why its name. It was a great, I think, a Greek mathematician Euclid, and based on his name, we call it Euclidean algorithm. And the purpose of that algorithm is basically to find this greatest common divisor, the mathematic function. And another person which is quite known in the history of algorithm is the Persian mathematician Al-Khwarizmi. He was the first man who wrote down step-by-step algorithm, because before that people have their algorithm, but they were not used to write down and document the algorithm. So and based on his names, when his name came to Latin, and it was transformed from algorithms to become the word algorithm. So this is just some basic facts about this. So and also an important part of algorithm is that we use algorithm to solve a problem. So that's also important, that you should not forget that you have a problem and you want to solve a problem, then you have a step of instruction. So it's in other words, we can say like an algorithm is like kind of a recipe. So if you want to cook something, if you want to make a food, you have a instructions given step by step. But in case of a recipe, you are more open. The recipe could be ambiguous as well. So there are no like formal requirements. But when it comes to the algorithm or the scientific methods, things that should be more precise, and there should be no ambiguity in that. And it could also be considered algorithm as like a user manual. So for example, if you buy some furniture, like a bed from IKEA, for example, then you know the IKEA delivers its products usually in pieces. So you have a lot of parts and pieces, and then together with those parts and pieces, you get a user manual and how to assemble that product. So there are like steps described, and then you follow those steps to assemble or combine, or to in that case, your problem is to assemble the product. So, and here we have a simple problem to wash the hair. So how do you wash your hair? So what is your algorithm for washing the hair? Can someone, how do you guys, what are the steps to wash the hair? Anyone? It's a simple problem. Water and shampoo, yeah. So you begin with pouring water, yeah. And then apply some soap or shampoo, yeah. And then clean the shampoo or soap. So yeah, as you said, that start by wetting the hair, pouring water, and then you rub some shampoo, and then. So if we describe this in terms of algorithm, so these are the different steps. So we start by wetting the hair, then we have a loop here. So maybe you have a quite messy hair, so you don't do it in one step. And if you have like a thick, long hair, people usually often clean, more than once. So you can have this repetitive steps. So repeat until the hair are clean. So you already know, being a programmer, I suppose that you know this iterative statement here. So you rub a shampoo and rinse shampoo away. So you pour water to get the shampoo away, and you keep on doing this, as long as your hair are not clean, and you are satisfied with that. And also there could be some optional parts. So if it's cold outside, and especially if you have a thick, long hair, and if you want to go outside after, then you also would like to dry your hair. So you might use a dryer. But if it's not very cold, maybe it's a summer and you want your hair to be cooled down, maybe you can leave it and let the hair dry by themselves. So so the basic thing is like you have a problem, and then you have some specific number of steps to solve that problem. Okay, and then here's an example, an algorithm to find prime numbers. So for example, you get a number, it could be any integer, 1, 2, 3, 4, or 100 or whatever, and you want to find out if it's a prime number or not. And before that, maybe it's important to identify what is a prime number. So anyone? What do you mean by a prime number? Which number is a prime number? Yep, Saprit. Yeah, exactly. So if a number that is that can be divided evenly by itself and 1, so there are only 2 possible divisors for that number. So and it's also said that it should be a number greater than 2, 2 or greater than 2, which is divided by itself and 1. So and here we have so algorithm to find out if a number is a prime number or not. And the basic idea is that you keep on dividing by the numbers until you don't find anything which is divisible. So for example, here we have algorithm for it. We start by checking from integer 2, and for example, if you have a number n and you want to check that whether it is prime number or not, so you take an integer variable with the name test, and you have a loop here, and the loop says that we keep dividing n by this test until as long as we don't get the remainder or the modulus is not equal to 0, and we do it and every time we repeat this test, we increment the value of test by 1. Okay, so let's say if you have for example, if we have a number n which is 6, and we want to find out if it's an prime number or not, so we start with we start testing by dividing starting from 2, and if you get here, because if you divide by 6 divided by 2, the modulus, the remainder you get will be 0. So in this case, here we say that while n mod not equal to 0, but in this case we get the 0. So loop will come to end here, and then we test if n is equal to test. What does this means? This means that every time we are incrementing the value of test, so unless we don't get to the number by itself, so we get, and if that's equal to test, it's a prime number, otherwise it's not a prime number. So in this case, because n is equal to 6 and test is equal to 2. So this condition will be false and n is not a prime number. On the other way, if you have here, if you have a number maybe, yeah, let's say 3 or maybe 7. So we go here, and when we divide 7 by 2, so we get the remainder should be 1. Okay, so in this case, the loop will execute, and we increment the value of test. So test was before it was 2, now we change it to 3, and we divide it, and here, what should be the result? Again, it will be 1 remainder. So, and then we go again, 4, and when you divide by 4, yeah, maybe you will get something like 3. And you will keep on doing it, and finally you will get the test will become 7. And when it becomes 7, you divide 7 by 7, the remainder will become 0. And in this case, this condition will become true. Okay, that's quite simple. So nothing complicated here. So we have already seen some parts of the algorithm definition, but here is more detailed one. As described earlier, it's a step-by-step description to solve a problem. And what is important is that it should be like unambiguous, and also not only the algorithm or the instruction itself should be unambiguous, but also the results should be unambiguous. What it means by results, like if you have, it should not be like if you run, every time you run that algorithm with the same input values, you get the same result. It should not be like once you, for example, if you have an algorithm for addition, and once you run that algorithm with an input 2 plus 2, it gives a 4, but the other time when you run, it may not give 4, maybe it gives something else, like 6 or 7. In that case, if you don't get unambiguous results, it means that your algorithm is not perfect or correct. And also an important part is that the number of steps should be finite, should be limited. It cannot be like a continuous operation. Then you will never come to an end. Okay. So in this case, for example, here we have an equation to compute the value of pi, a mathematical symbol, but then here you see that it's a continuous operation. There are infinite number of sets. So in that case, this cannot be transformed into an algorithm. But we have seen algorithms, what an algorithm is, and we got some understanding about that. But then maybe a question comes, why we need algorithms? Anyone? Why do you need the algorithm at all? To find a solution, yes. If you have a problem, you want to solve it. And other than that,
programming is we're not writing the same code each time.
Sorry?
In programming could be we're not writing the same piece of code each time we want to achieve.
Okay, yeah. So depending on different implementation, if you could have a different ways to solve a problem. Yes.
To have a precise solution.
Yep.
To solve problem every time we repeat it.
Yes, all of them are correct. And here are some further reasons why we need algorithms. So first of all, we need an algorithm to document the solution. Okay, so can think something like this. So if it's a new problem, so think yourself that you are like maybe if you are living in before Christ times, and in the age of Al-Khwarizmi and other mathematicians. So, and you come a problem and you want to solve, and you have solved that problem for the first time. Okay, and then you want to document that problem so that you can present that problem and you can communicate and distribute that problem to other persons, because otherwise everyone will be solving that problem by itself. Okay, so we need algorithm to document by the instructions, to communicate, okay, and also to compare the different solutions. Maybe every person, as you said, that there could be different implementation. So one problem can be solved a number of different ways. Every person can come with its own implementation. And then if you want to compare which one is the best algorithm, And to make the comparison, you need something like algorithm. Okay. So once you have, if you have not documented, if it's only in your brain, then you cannot compare with others. So to make a comparison, you also need algorithm documentation. And also, it's also a good idea. Common practice, I think, when you are learning programming, it's often that you get a problem and you go to the implementation. You don't go to this algorithm step. However, it's always better that whenever you have a problem, for example, if you have a different task in an assignment, so it's good that before going to implement that problem or solution for that problem, you first take a paper or a board or something, and then you try to make a design of that solution. So sketch the different parts, and it's like a preparation or the design of your implementation to solve a problem. So, and those kind of sketchy steps can be later on transformed into a more formal algorithm. And here we have another problem. Sorting a deck. That's another example of an algorithm. So how do you sort a deck of cards? Okay. So maybe the one algorithm to sort the different cards or the deck of cards is that, as you know, that we have like 4 different colors or the piles or the suits in a car in one deck of 52 cards. So you begin with sorting them in colors, and then for each color or each pile, you sort the cards by rank. Okay, like you have. I hope that you will be familiar with the cards. So you have a card starting from number 2, 3, 4, the ranks, and then it goes from Jack and Queen, King, and Ace. So, and then you sort them by ranks, and once each pile is sorted, you collect them together to get the whole deck. Okay. However, if you look at this algorithm, is it precise? Is it ambiguous or not? Any idea? Yeah, the problem with this algorithm is that it doesn't have a concrete description of steps. It's more like an outline. It says that sort the colors, but it doesn't describe how should. It describes what to do, but not how to do. And the algorithm is like more like the steps how to do, and and it says the problem with this is like it doesn't give you any specific instructions, like how should you sort the colors and how should you sort the different cards by a rank. Should you start, one person could start from the larger side, I mean the king or the ace, and another person can start from the middle, another person can start from the smallest size, and one person can start with the clubs and the diamonds, the different card types. So in this case, it's more like an outline, but it's not like a precisely or unambiguous algorithm. Okay. And then, so then will come a question. Does the above algorithm describe an implementation? Does it? Can you transform this into an implementation? Any guess? I think I already given you the answer. So since it's an ambiguous one, so we cannot really. This type of sketchy algorithms are, it's good, as I said, that it might be a good starting point because it outlines you, and you can take then these steps and further describe those steps. So it can be refined later on to a complete algorithm, but it's not like a complete algorithm by itself. So it's a starting point which you can later on extend to build a more complete algorithm. Okay, and to write down, to document an algorithm, there is no standard actually format. So, and commonly we use 3 different formats. The first format is you can use the simple language that you speak. You can write an algorithm in your mother tongue. If you speak English, German, French, Urdu, whatever you speak, you can write the instructions of the steps in your own language. And the advantage of this ordinary text is that it's, if you, for example, if you write in English and almost everyone understands the English, so it's, the advantage is that you can have a larger audience that can understand your algorithm. But however, as the problem with the natural languages is that the natural language is something that you write can be interpreted differently by a different person. So there is no like formalization in a natural languages. So it could be, yeah, if you write something, but another person which uses your algorithm could implement it in a different way. So its ambiguity is still there. And if you use the programming language, which is the opposite to the ordinary text, programming languages, the advantage is that they are very precise according to their syntax and the grammar defined. And there are also another advantage is if you have written an algorithm in some programming languages, you actually get an implementation. So you don't need to get to later on to implement that algorithm. And however, a disadvantage is that it requires that all your audience for which you are documenting, they should have a programming knowledge. So they should understand they should have if for example if you have written an algorithm in Python, Java, or C#, so your audience should know that language. Otherwise, they will not be able to understand it. And and the third form is it's a mix of both ordinary and programming language that we call a pseudocode. Advantage of this is that it's, for example, if you compare this with the programming language, pseudocode is not coupled or dependent on the knowledge of a specific programming language. So it's more like somewhat in the middle of both ordinary text and if somebody understands the basic mathematics, because in pseudocode format you basically use the notation and the symbols from mathematics and some of the symbols from the programming concepts and some keywords are not the keyword but the ordinary text words. Okay, so it's easy to understand, both for a general audience and also for the programmer as well. So if a guy understands the programming language concepts, he can understand the pseudocode quite well. And it's also, if you compare, sorry for that, I just have to, no. And if you compare this with the ordinary text, so ordinary text is written in an ambiguous way, so it's not easy to implement. But if you compare this with the pseudocode, it can be easily transformed. Okay. Yeah, and here are some more details about pseudocode. And as I said, that it's a mix between ordinary and programming language. However, it's more precise, and it could have the primitives like if, while, for from the programming language concepts, and it could also have mathematical symbols in it. And what is important for the pseudocode is that it should be able to handle the following 4 constructs. And these constructs are basically like you have in a program, you have like steps or sequence of instructions. So it should support something which is written as a sequence of instructions, and then selection statements, so that you can select the different parts of the your program, so depending on different conditions, and then iteration. So you can and it should split the simple arithmetics like plus minus. And if any system, because these 4 steps are the different constructs, they are said to be the basics of any system or any computing system or a language. If a system or a computer system, or doesn't matter, I mean, computer is more like a general word of a system that supports these constructs. And if you have a language that supports just these 4 constructs or features, then you can solve any problem with just using these features. Nowadays, I mean, you have very advanced features. You have a generics, you have APIs, and you have inheritance and object orientation. You have implements, extends, keywords, and blah, blah, blah. But even if you don't have those advanced features, if a language supports only these, you can use it to solve any problem. But it might be like your program might be not in 2 or 3 lines. It could be quite long, depending on, because you don't have very advanced features. And so and if any system that supports these 4 constructs, we say that it's a Turing complete system. So Turing complete, I guess you guys being a computer scientist, you know that Turing machine and the Turing complete properties. So it was named after this I think English a mathematician and computer scientist Alan Turing, who invented this Turing machine. And the Turing machine satisfies these properties, and based on those and any algorithm that satisfied this constraints and then support these constraints, we say that it's a Turing complete algorithm. Otherwise, and the pseudocode that supports language that supports these constructs, we call it's a Turing complete. Okay, so here we have some example for the pseudocode. These are more like, it's basically you already seen the examples when I give you the algorithms examples. But just to give you more description, I mean, there is, as I said in the beginning, there are no exact rules for writing the pseudocode. So there is no like standard format. You can come up with your own kind of a pseudocode format. And there are two examples. So we have a for example, we have a problem that we want to find that can n be divided by 3. So you get a number and you want to find that is it divisible by 3 or not. And you are supposed to write algorithm for this problem. So you can write the algorithm using this method, structured ordinary text. But if you look at these two methods, the problem with this one is, although it's acceptable, but it's more like more text oriented. You have a more details here. But if you look at the method 2, it's more like a programming syntax, and it's more precise and suitable for programming. So, but it's up to you. You can use any of these two methods. So, but mostly if you prefer the programming, if you have a good strong background in mathematics and programming, maybe you will prefer the method 2. But if you don't really like these mathematical symbols and stuff like this, so maybe you can choose with the method 1. Okay, so problem solving algorithms. Okay, and also with this algorithm, because we said that algorithms are used to solve the problem, and so the important part in the algorithm is a problem solving. Okay, and then I have a question. So if you, for example, what is your approach to solve a problem? If you get any problem, a general problem, how do you solve a problem? Not really according to this. I mean, of course, you can think about in terms of a programming. Program implementation, but you can also think about a general problem in a life. So for example, if you want to find a job, that's a problem. So how do you solve a problem?
First you need to define the requirements.
First you need to define the requirements. Mm-hmm.
And then you have to think about taking steps and fulfilling those.
About steps.
Yeah.
So you need to identify or define some steps.
To accomplish that.
And then
And then do it.
do it. Yeah, more or less the same as we have the answer over here. So one of the famous steps, I mean the earlier one, these were given by this Hungarian mathematician named with George Pulya, and it's commonly referred as Pulya's 4 steps problem solving approach. And the first thing, whatever kind of problem is, it's all very important that you need to understand the problem. So you analyze, you read about the problem. What is your problem? Sometimes the problem are very tricky. They are very difficult to understand by themselves. So if you don't understand the problem itself, and if you don't understand the reason or the factors that are causing the problem, you will not be heading in the right direction. So the important step is that you spend some time, spend some hours, and as you said, that identify the requirements. So, and often, being a software engineer, the computer scientist, you know that requirements are already always often tricky and ambiguous. So the customers, when you go to the customers and if you ask them about the requirements, often the customer don't really know what they actually require and how they describe the requirements in a bit different way than actually they want the system is. So the first step is whenever you have a problem, so spend some time to understand the problem, and then once you have understand the problem, you can proceed with the second step, as you said, that you can write down some steps. So devise a plan, so make a plan. So the planning is more like an algorithm. So you write your algorithm or a plan to solve the problem. And once you have written, well, once you have a plan, then you go with to implementation. And after that, once you have implemented it, it could be that you have solved the problem, and it could be that your implementation was not successful. And in that case, you can look back and think and start by maybe you misunderstood the problem, or maybe it could be like from here you can go to maybe this step, or this step. So it depends on what kind of results you get after the implementation. And similarly to, based on those PolyJazz 4 steps problem solving, we could have a problem solving with the programming. So as a programmer, we could also have the similar steps, like as I already described that this create an algorithm is more or less develop a plan, okay? And then you implement, and once you implemented it, so basically when you are testing it, you are kind of reflecting over the implementation. And then, with the algorithm, and also an important thing is you guys, I think, often heard about this divide and conquer approach, or divide and conquer algorithm. And this approach is pretty useful if you have a very complicated problem. So in case of complicated problem, there are problems that you cannot solve in a single step. So then you can, if you are this much. You have a system. Often you do when you have a problem, or when you are doing this, if you are developing a project, so you can divide your problem or the system into subsystems or the sub-problems. And then you can assign those problems, maybe if you are the only guy that are developing the solution, so then you can divide the problems in a number of hours or days and work on them. And if you have multiple people working on that, maybe you can divide and distribute into different people and the members in the teams, okay? So larger problems are divided into smaller problems, okay? And and even the smaller problems can be divided into one step more smaller problems. So until you get a granularity where you can a problem can be addressed, okay? So it's a good approach. It gives a structure to the problem. So you have a specific structure where you start from a bigger problem, then you go smaller until you have a solution. So for example, you have a problem 1 here, so you refine this problem 1, and then you have like problem 2, and at each step you are refining it. So let's see, here we have an example, okay? So the problem here is a quite simple problem, not from the programming but daily life. So after the dinner, you need to clean out or wash the dishes. So do the dishes. How do you do the dishes? How do you clean out? Okay. So here we have a basic 3 steps. Rinse away the leftovers. And then clean or wipe the dishes and then clean up. And then, for example, how can you do the dishes? So this is like a more bigger problem. And we have refined this. Okay, starting with the wetting or pouring water, apply some detergents, liquids or soap. Wash all the items, and this wash all the items, maybe we have refined it more in sub steps, okay? Repeat until no more items. For example, if you have 10 plates to clean out, so you start by one by one, and put in water, brush it and rinse it, and then put it up to dry, okay? So that's like a divide and conquer. So, and that's from the, I think we often do this in our daily life. So whenever you have a problem, so if, for example, if you have a large set of laundry clothes to wash out, which you cannot do it in one go, you can divide into smaller parts. For example, if you need a shirt tomorrow for a presentation, so instead of washing whole clothes, you just prioritize your task and you do it. Okay, and it's also sometimes another important idea is that sometimes instead of when you have a problem and you have a general description of a problem, and instead of looking at the description of the problem, if you somehow can get an example of that problem, and then you can understand the problem better than the problem itself. Okay. So for example, if you have a problem of adding the 2 integers, okay, in this case, that's a general description. But if you get the example like 13 plus 25, that's my problem. And if you know the mathematics, you will quite quickly understand what the problem is and what I need to do to solve this problem. And the same is like if someone says like sort a list with the names alphabetically. The problem is that a user wants you to sort a list of names according to the alphabetic order. Okay, yeah, if you know this, maybe you can understand it. But if you get this list as an array of names, and if someone asks you to sort this list, yeah, so you will understand it quite quickly. So, so whenever you have a problem, try to, before addressing the problem, or when you are doing this understanding and devising a plan and kind of coming up with the algorithm, it's good that if you take the instance of one example or one instance of a problem and see how does that instance looks like and what are the problems in that instance. So for example, if someone asks you to write a system that's for employee management system or payroll system, so that's, and then you have a general, guy can give you a general requirements, but then if you go to the actual some kind of a actual company or an organization and see their system and read their system, then you will get more details how that system is actually working in practice instead of just some instructions written in a report or a document. Okay, so yeah, so a general advice is that whenever you have a problem, so begin with the number of instances and look at 2-3 different instances, and then by looking at and analyzing those instances, you will get more understanding. And once you have a more understanding, it's then you can attack the problem by itself. So, and later on, you can use that instances to verify or test your solution as well. So if you have an example, you have already got the examples, and then you have solved the problem, you have a solution, and then you can test that solution, does it fits or satisfy, solves these the instances or not. And if that sorts, if you have tested it for, I think we already have a lecture about testing, so you can have these extreme cases and different cases to identify and to check the correctness of your solution. Okay, and then when we was talking about why algorithm, so we discussed that one of the reasons about the algorithm is that we want to compare the solutions and to find out that if it's a good algorithm or not. But how do you know if it's a good algorithm or not? What should be the criteria? Someone? Sorry? Complexity, yeah, if it's complex. And what do you mean by complexity?
Well, it's too complex if there are some ways to make it more efficient than
You mean complexity in terms of understanding or something else?
understanding and running.
Understanding and running, yeah. So if it's taking more time and if it's running slower, then maybe there could be another algorithm that, for example, you have solved a problem, but it takes too much time. So it maybe takes 10 minutes to sort a list, but your customer is not happy. He wants something that can sort it in just maybe a minute or so. So then maybe you have to, so to find out, to get if it's a good algorithm or not, yeah, so there is some criteria. And first, some basic criteria is that, yeah, it should be correct. So it should give a correct solution. It should not give a false or a wrong solution, because otherwise then it's no use of your algorithm. But there might be more than one correct algorithms. So as I said, that there is an algorithm which sorts a list, but it takes 1 minute. Then there is another algorithm that takes maybe 10 minutes or maybe few seconds. Then you have a different implementation. So, and then you have some of the possible criteria to compare which one and pick the best algorithm. Depends on, of course, depends on the best algorithm depends on your definition of best. Okay. So, for example, if you want something which is fast enough, then you have to think about this resource time efficiency. Okay. And but if you want something which is which doesn't cost a lot, that doesn't require more resources, then maybe you can go with an algorithm that takes maybe 10 minutes, but it costs you only maybe $100. But on the other hand, there might be a faster algorithm, but it takes more money. So these are trade-offs. So, and the different algorithm could have different performance, and So when we are comparing the algorithms, we check that all those algorithms are correct, and yeah, some basic criteria are that they should be simple to understand and implement, so they should not be like overly complicated, and cleanly written and well documented. And yeah, apart from that, we would like to have the efficient algorithm. So, and yeah, as you mentioned, that efficiency means that it could be resource efficient, and it could also be the time efficient. And the resource efficient means that it consume limited or the less number of resources, so it doesn't require too much memory space for its operations. Because if it requires too much memory, too much other devices, CPU time, and other network devices, then it means it could cost a lot. But on the other hand, you could also require something time efficient, which performs an operation or solve a problem quickly. So in this case, we call that it's a time efficient algorithms. And in today's lecture and in this course, we will focus more on this time efficiency part. But that doesn't mean that other parts are not important. They could be vital as well. However, we could not cover on everything here, but in this lecture we will be targeting more about time complexity. Okay, and yeah, and to find out the time complexity, we will basically use this asymptotic analysis approach. But before moving on to this time complexity and asymptotic analysis, I think we take a 10 minutes break, and after the break we will continue with that. Okay. So we meet again at let's say 2:05. Just 1 minute. Okay, coming back to the lecture, we talked about how can we find out what is a good algorithm and what is not a good algorithm, and we discussed about the criteria. And in this lecture, we will be targeting about more about the time efficiency, and to analyze the time efficiency or the time complexity of an algorithm. One of the approach that we use is asymptotic analysis. And this is not just a computer science concept, but it's more like a mathematics concept. Does anyone already familiar with what asymptotic analysis is? If you have studied mathematics or calculus, maybe, yeah? Runtime. But
if the input is smaller and very big, it should not affect on the time complexity.
no, not the other way around. Yeah, asymptotic analysis is especially you use the asymptotic analysis if you are interested to find out the performance, or if you want to analyze behavior of a system when the input size is bigger one. It's when the input size is quite big, and if you want to study how does a system performs when it comes to a large set of data, like almost reaching to infinite size. So then we use asymptotic analysis. Okay, so as you can read down here, behavior when the input size is big. Okay, we are not interested in a smaller cases, because yeah, smaller cases, trivial cases, you can solve. An algorithm can solve. For example, if you have an array of only 3-4 elements, and maybe even a worst algorithm can sort that array or search elements in that array in a few seconds. But what if the number of elements grows? If the size of the list, or if the data in a table or a database grows, so how will your algorithm will scale, how it will perform? And to identify and to analyze the performance of your system or algorithm on a larger set of data, we use this asymptotic analysis approach. So basically, and yeah, and when we are using this asymptotic analysis approach, we are not taking into account that which computer machine you are using. We do in general the analysis, so it's not depending on any specific machine. So it's more like independent of the machine that you use. And yeah, we use it to answer the question like which of these two algorithms are faster if the input size is big. Yeah, that's the basic point. And also, like, maybe if you want to answer a question like how an algorithm will perform if we increase the size of the input 2 times. So for example, if it takes 5 seconds to sort an integer array of size 100, and how much time it will take for the array of size 200. Okay, so that's something related to the input size. So, and yeah, and we can find out this by analyzing the time, as I said in the beginning, that the focus will be on the time efficiency. And the time complexity, basically it's an estimate of required time to solve a problem. So for each, if you have 5 algorithms, then if you want to find out the time complexity of those algorithms, you need to measure or estimate how much time each algorithm takes to solve that problem. Okay. So and usually it depends on the size. So for example, finding an integer in a list, time depends on a list size. If the list is smaller, you can search or find quickly. But if you have a size of thousands, it will end. For example, you start from the beginning, searching from the beginning first element, and if the element is the last element, then you have to go from 0 to until last. So it will take almost the n number of times. And also, if you want to find a prime number, yeah, it will also depend on the size. So for example, if it's a smaller, so for example, when if it's like a number is 7, you will maybe find the number after 4 or 5 steps. But if it's some bigger number, larger than 100, then maybe you have to perform more steps. So the time will depend on the size or the number itself. and the same is on if you want to sort out. Okay, and we say that an algorithm have a time complexity big O. Yeah, usually if you pronounce this this notation, it's time used for the time complexity, and you can say it's also like O of n. But correctly speaking, it's technically it's known as big O notation, and sometimes we also call it Ardo of. In the computer science, we normally call it big O, but in mathematics, it's often known as Ardo of. And yeah, so the time complexity will be yeah big O n size n if computation time is proportional to n. So it means that if the size of the input increases and the complexity or the time to solve that problem is directly proportional to size n, then its time complexity is big O of n. Otherwise, the time is proportional to the n square, then the time complexity will also become n square. And if it takes a constant time, if it doesn't depend on the input size, for example, if a program takes to sort a list of size 3 elements, and it takes the same amount of time to sort a list of a size maybe 1 million or 100 or thousands, and if the time is constant, it takes the same amount of time to solve smaller and the larger values, then we say that the performance of that algorithm is a constant, and its complexity is for those constant times, the complexity is represented as time complexity will be represented as big O of 1. Okay. And in general, so these are just the examples, but there could be some other time complexities as well. So for example, some logarithmic complexity. So and maybe it's like exponential complexity. So you can consider this as your methods or as your some functions. And in general, big O time complexity will be function of input size n if computation time is proportional to function of input size n. Okay, so whatever when you have algorithm or implementation, so you try to analyze the behavior and try to find out that how much time it will take, and will it take the same? Will the time if the time depends on the input size directly, then we have the time complexity O(n). If the time is if the time increases as we increase the 2 times of the size, then it's n square. Okay, and if it's the constant, then it's simply O(n), O Ardo of 1. And when computing the time complexity, we assume that each simple computation takes just 1 second, 1 unit of time. And what does the simple computation mean? Like just our basic arithmetic operations like plus, minus, and assignment statements and multiplication, division. So, and you can assume that each of that statement will take just a constant time, 1. So here we have an example. So for example, we have a method, and if you want to find out the time complexity for this method, which takes an input value, integer value n, and it prints the table until, for example, if you have a number 5, so it will print the table of that value starting from 1 until 5, and if you have a number value 10, it will print the value until 10. So we have this method written here, and so it starts from 1 and then it goes until that number, and it prints multiplication like square time values. So we have 2 inner loops, and in the inner loop we are printing the result of, okay, so of that table. What will be the time complexity of this method? Any idea? Square of n. Why? Sorry? Yeah, exactly. So to estimate the time complexity of a method or a program, you find out the part of that program which executed most number of times. Okay, because Here we are concerned with the time complexity. And then and we can find out the time complexity by finding out the statements are part of the code which execute the most number of cases. So we are interested in the worst case. The one that takes the smaller number of times doesn't matter. But the part that takes the highest number of times are the statement which is executed more. I mean, the general rule is that if a statement is being executed more and more again and again, then it means that it is generally supposed to take more time. Okay. So here we know that this statement will be executed roughly almost n number of times. So then its complexity will be n square, because so if you have for example, if you have two or three loops that have been inner loops structured as, so because once this executes, every time this loop will be executed n number of times. So that's why we have a time complexity equal to n square. Here we have another method, and that is for searching an integer or an element within an integer array. So, and we start from the index 0, sorry, and we compare every element with the given value. And if the value has been found, like if it returns the same element, we return true. Otherwise, we check from 0 until last index. And if we find the element, whenever we find, we return. Otherwise, we find the false. So what will be the time complexity of this one? So for example, here I have an array. Okay, size 4, and I have some elements like 2, 4, 1, and 5. So, and I want to find out, yeah, I need to take some better, and the number we want to find is, for example, 1. Anyone? Yes?
O1.
O1. Why?
Because you search for it the worst possible scenario, which is the number being the last one.
Number being the last one, or maybe the number which is not even in the list. Okay. So for example, I mean, it could be in a best case. So for example, if you are looking for a number 2, in this case, you check the first element and you find the number. In this case, it will be very fast. You don't need to check the whole list. Here, for example, here, very small list, but you can have a list of maybe until, yeah, size 1000. And in that case, if you are lucky enough that the element that you are looking for is at the first location, you will get that element in the first iteration. Okay. So when you execute the loop for the first time, you will get the element that you want. But on the other hand, it could be that the element that you are looking for does not even exist in that list. So for example, if we have this list, 4, 1, 5, and the element we are looking for is, for example, 20, then you go, but you will go and check every element. You have to visit every element, and it means that for every element, I have to execute this part at least once. So it means then the time complexity is proportional to the size of the list, because I have to perform that operation 4 number of times. If the list size is 4, I have to perform this 100 number of times. If the list size is 100, I have to perform this 100,000 times if the size is 100,000. Okay. So often, if you have a linear search algorithm, so the time complexity of linear search algorithm will be O(n). Okay. Yeah. So here we have some more examples, and when we use this asymptotic analysis in practice, so we say that yeah, we assume that time complexity, yeah, is n, and here n we use in terms of input size. Okay. And as we told you before that in the asymptotic analysis, we are specifically interested in big size of input when the input size is big. And when you are estimating your time complexity, the constant factors doesn't matter. Okay, so for example, here you have if somehow you have computed the time complexity in very precisely, and the time complexity is 3 multiplied by input size n. However, you can specify this simply by removing this constant factor, because when we are estimating, because that's a constant factor, it doesn't matter. Still your time that an algorithm takes when you are comparing different algorithms will be proportional to the input size n. And also, if you have a time complexity expressed in an expression which is a sum of several different expressions, and in that case, we will take only that part which shows that takes more time, higher time. That shows that the computation that takes more time. For example, here we have a time complexity which is like 4 n raised to power 4 plus 45 n raised to power 3, and 102 multiplied by n plus 5. So, and which one part here will be the most time consuming? N raised to power 4. Okay, so we can ignore the constant, we can remove the smaller terms, and we can simply say that the time complexity estimate. This is an estimate. Remember, this is not like a precise. This is more like an estimate of in terms of asymptotic analysis. So O n raised to power 4. Similarly, here we have 16 multiplied by n and 3 log because you couldn't have any mathematical functions when computing this time complexity. So here it's log of n plus under 2. We ignore the constants here and here, and which one is the fastest growing? The fastest growing is this part, n multiplied by log 2n. Okay, so this is more like a logarithmic complexity. So where the time that an algorithm takes is a logarithmic function of your input size. And what about this case? Which one is the highest term here? Fastest growing term? Last one. Okay, so you should not be confused by this. It might, in the first attempt, it might look very temptative that n raised to power 88 is largest one. Okay, and so as I already described that here, this time complexity estimate is when you should, as you told that we care about the worst scenario, and in this case, in the input size case, the worst scenario will be when the input size is very large. Okay, we are always interested in the worst case scenario. Okay, not when we are finding an element at the first position in the list. Okay, so you should not. I mean, you should not. If you are considering and comparing using the asymptotic analysis approach, then you have to take account the larger, the worst case scenarios, not the simple cases. And here are some frequently used big O expressions, or the time that are used to compare and analyze the different algorithms. And you can use these notations, these expressions to compare algorithms. So for example, you are working in a company, and a company asks you to implement some method or feature that gives the best performance in terms of time to find employees in his database. And then if you have a different algorithms with different time complexity, and you want to find out which one is the best or the efficient or the fastest algorithm, you need to go to those algorithms and check their time complexity. And the algorithm with the fastest time complexity, or the time that takes lowest times, you can choose that. Whatever algorithm you find, you will often find in their documentation. You can find how much time it takes, or what is the time complexity associated with different algorithms. So, for example, you can have a number of different algorithms for sorting. So we have, if you know that we have if you have studied some algorithm courses, maybe you are familiar with the selection sort, insertion sort, quick sort, merge sort, heap sort, And similarly, you have a different algorithm for searching. So for example, you have a binary search algorithms and you have a linear search algorithm. So, and then you can compare. So we will talk about some of those algorithms in today's lecture as well. And here, if you look at the top, we have the fastest time because this one always takes a constant time. So, and then we have a logarithmic, and then we have a number of size, and then the bottom, since it's like a polynomial, or so 2 raised to power n, so that will be the most time-consuming algorithm. So as I earlier mentioned, that we usually have to, one of the common operations in a computer science is this searching. You often have to search data, and you often also have to sort the data in a particular order, either alphabetical order or maybe ascending, descending orders. And so in these lectures, we will see about few algorithms for the sorting with this time complexity. We will particularly talk 2 algorithms with the time complexity, which is n square. That's quite time-taking algorithms. And then we will have a much better algorithm that has a lower time complexity, which is logarithmic. And then we will also look at 2 such algorithms. So selection sort, one of the simplest and the basic algorithm for a sorting. Can someone explain what is selection sort and how does it works? Anyone? How do you use, what is the mechanism behind the selection sort? If you have a data, if you have an array, integer type array, and if you are asked to sort that data, how do you sort it? Not forget about the selection sort. If you have in general, for example, if we have this, let's say we have, one more, and we have like -5, maybe not -5, 5, 2, and 8, 1, 10. And if someone asks you to sort this array, how will you do that? What will be the basic algorithm? Sorry?
Independently from selection sort.
No, independent of selection sort. Your algorithm. What will you generally sort an element? What will be the basic step? If I ask you to sort this in ascending order, smallest element first. Sorry?
Find the smallest.
Find the smallest and
The list and swap it to first.
swap with the first one. Okay? So you go through all the elements in the list and find out which one is the smallest, the other lowest value. So in this case, we have this one, and we will swap these 2. So we will move, a general approach will be like we move them. 1 will become here and 5 comes here. And then, since you know that you have already sorted this part, so you start from here, and here you will check which one is the smallest element. 2 is the smallest element, so 2 is already at its right place, so you don't need to swap in that case. Then you have sorted until here. You check these elements, pick the smallest, sort it. Okay, so this is actually your selection sort. Okay, so there is no rocket science behind selection sort. So it describes here, find the smallest of the numbers and swipe with the first place, and then you find the smallest of the remaining n-1 elements. n-1 because you have sorted already one element, so then you have to don't have to sort that again and again. And here is just an example, so similar to the one that I shown it here. And here we have an algorithm for selection sort. So for example, let's say we have a list L starting from index 1, not from 0, in case of this algorithm, and until the size n. So we can, what we need to do is, for each element I that belongs to this array list from 1 to n-1 elements, and to find out the smallest element, we need to find the index. And in the beginning, we assume that p is equal to I, so starting from the first element, and then we go through all the remaining elements, and we check if Lj, and here the j is starting from the same element, and we compare, and if you find a new smallest element, you replace p with the new smallest element. So in the beginning, we assume that our first element is the smallest element, but later on, if you find another element which is smaller than the first element, then you update the value of p index. And in the end, we just swap the values. So this case is, this code is just swapping the values with each other, okay? So, and now if I ask you, what is the time complexity of this algorithm? How will you estimate it? What is the important part when you have to estimate the time complexity? Nested loop are part that is executed most number of times. So, and usually, usually if you have a code or program which has nested iteration, so usually that part will take. So simple is that you go there, and since this part is executed more or less n square number of times, so then it means that time complexity will be on O of n square. But we have some better algorithm than this one, so we will talk about that algorithm later on. And another, so that's just Java code for the selection sort, so it's nothing complicated here. And then we have insertion sort here, and the basic idea in the assertion sort is, because in the selection sort, what we was doing, we were starting from the first element, and then we were comparing, finding out with the other elements, and try to find the smallest and swap it with the first element. However, in this insertion sort, it says that put the second element in the right position among the number of elements. So let's see, looking at an example, maybe we have an example here. So we have, let's say we assume that we have a list here, 6 minus 7, and we want to sort it. So the algorithm says that put the second element in the right place. So start from the second element and see if it is at the right place or not. And how can you see? And also, it's also important for the insertion sort. In the insertion sort, we assume that if we are starting from the second element, we assume that the first element is already sorted one. So the part on the left is already sorted. We assume that, and part on the right is the unsorted one. Okay. So in this case, and then we find the right place for minus 7 in the sorted list here. We compare with this one. So this is smallest one. So we just put it in the right place. The right place is before 6. So we add it here, and then we continue with the third element and find the right place. So it's already on the right place. So we don't make any changes, and then we fourth and so on until the last element. So for example, after 9 we find the minus 12. Okay, and so the right place for minus 12 is in the beginning because it is smaller than all the elements. Okay, and so in this way we keep on until we find the last element. So and also it says that when you are using the insertion sort, assume that the first p elements are sorted. Okay, and then the remaining p plus 1 element to the left, if they are not until you find a suitable place. Yeah. So what will be the time complexity of this algorithm? Same. Why? Because it iterates. Almost, because we have to start from the second place and go to until, and in the worst case it could be like we have to n number of times, n square times. Okay. So there is, if you talk about in terms of time complexity, both insertion sort and selection sort have a more or less same time complexity. Okay, so here we have a selection sort versus insertion sort. So there is only some differences that in the selection sort, every time we pick smallest value and swap it with the first element, okay, in the list. And but in the insertion sort, we start from the second element and put it in the right place, and then we go on. Okay. However, which one is the best? If someone asks you which one is the best, selection sort.
Yeah, I'd say insertion.
Yeah, someone says it's selection, someone says insertion. So who said? Because I did not notice. Why selection sort?
It takes less time
It takes less time. How?
compared to the insertion. Insertion, you need to go through all of them.
Mm-hmm. But the time complexity of both is O n square. Then doesn't it mean that it will take same time? Yes?
Because the best assumption may be different. Selection might be both might be O1.
Mm-hmm. Both might be O1.
Yeah.
You mean like constant?
They might be already sorted.
They might be already sorted, yeah?
But the thing is that with insertion sort, you have to do more operations.
More operation.
During that.
Mm-hmm. And why you said that? Yeah. Why you said that? Oh. Yeah. Why you said that? Why you think that insertion sort is better than selection sort?
Well, if two elements next to each other are already sorted,
Mm-hmm.
if the smaller one is on the left side,
Mm.
there is no need to do changes.
Mm.
It
Yeah.
just moves.
Yes. Yeah. I mean, if you have an unsorted or random kind of a list, then in terms of performance or time efficiency, both insertion sort and selection sort are more or less same. But special case is if someone asks which one is the fastest on an already sorted list. If you have an already sorted list, and then if somebody asks you to use which one is the best, selection versus iteration, then insertion sort will perform better on a sorted list, because in the insertion sort we already assume that the array on the left is already a sorted list, and once you have identified and the first element is at the right position, then you don't need to compare with the other ones. Okay, but on the other hand, if you have a sorted list but in a opposite order, for example, you get a list in a descending order and someone asks you to sort it in a ascending order, then insertion sort will require more swaps, because then you have to shuffle all the elements. So it depends. Okay. And then we have something about searching, and what is the basic algorithm for searching? So, for example, I think we already have discussed this. So to find an element in a list or in an array, you need to check every element and compare with the value that you are looking for. Okay, and this kind of searching approach or the searching algorithm is known as linear search, because we are in a linear way starting from a 0 index until the end of the list. And the basic idea is that you compare, return first position, and if found otherwise, yeah. So that's so here we have a method with the name of linear search, and if it finds the element, it returns the index of that element. Otherwise, if it doesn't find, it's done just as a flag value -1. So what will be the time complexity of this one? Which one is the most time? How many times this part will be executed? Yeah, the number of the elements in the array, the size of the array, so it's O of n. Now the question is, do we have a better algorithms? Yes. For can we use it for any kind of? Can we use the binary search on an unsorted list? No. Okay. So if you have a if you have a sorted data, if you can if you assume that, or if you make a precondition that before searching a list, the list must be a sorted list, then yes, we have a better algorithm in the form of, as you said, that binary search. But if we want to have an algorithm that could search in any kind of array, in any kind of list, whether it is sorted or not, then the answer may be no, because in an unsorted list, you have to visit and check every element and see if it is the element that you are looking for or not. It's like, for example, if the books in the library are not in a sorted way, and if you want to find a book that, for example, a Java book by a specific author, then you have to visit to look at every book. And if you are lucky, maybe you will find a book that the first book that you hit, or maybe after 5 books you will find. In the worst case, maybe you have to look at until the last book, and then you will find or maybe even after looking all the books, if the library does not contain that book, you will not be able to find that book. So, but if the books are in some order, in a sorted, maybe by author names or subjects name, then you can quickly go to that particular part where you have books on Java or books on mathematics or computer science, and then within that portion, maybe you have according to the books names or titles or the authors or the years, so different orders, and then you can find out. So, yeah, as you said that the better algorithm is the binary search. However, it requires that the assumption is that the list must be a sorted one. And the basic idea of binary search is that we take, for example, here we have this an array, like it should be sorted one. So I 2, 4, 6, 8, 10, 12. And the number we want to find is, for example, let's say n is equal to, we want to find 2. We take the array and then we find the middle element and check if the middle element is the one that we are looking for. Then we just return that element and the position of that element and stop. We don't need to do, because we have found the element in the first go. Otherwise, if the element at the middle is, if the element that you are looking for, 2, we are looking for 2, and we check the element in the middle, in this case, you can decide which one is the middle. You can either pick this one or this one. So normally we take the middle by using, So here we have, for example, we take the middle by dividing by the size by 2. So the size of this is 6. So 6 divided by 2 will be 3, and 0, 1, 2, 3, 4, 5. So our middle element will be 8 in this case. And we compare the value of 2 with this middle element. And if it's the value we are looking is smaller than the middle element, then it means that we don't need to check these elements on the, and even the middle element. Okay, we need to look to the left side, because on the left we have a smaller elements. And if the other ways, and we do this again and again until we find the element. So for example, here we have, if we want to find the 8, so middle element is 7, and what the element we are looking is 8. So we need to look it on the right side, and in the right side we find that the middle element is 9, and then we need to look it on the left side, and in the left side now its only element is 8, so the middle will be the same. So then we return the middle element. So this means that we divide our problem into halves. And once we divide the problem into halves, it means that we don't need to look into the other half. And that means that it will be definitely faster than our linear search algorithm. So usually, if the size, I mean, of course, the binary search is also a function of size. However, it's a little bit different than linear search. We usually say that if the size is equal to 1, we will find the first time. So the number of times required is 1. If the size is 2, yeah, we have to look at, because it could be on the left or on the right. And if the size is 4, yeah, maybe we have to perform 3 checks at 3 times. And size 8, 4, and so on. If you go here, if you try to identify the pattern here, the pattern here is the time is proportional to the 2 raised to power p and p plus 1. So for example here, 2 raised to power 3 will be the 8, and 3 plus 1 is 4. So, and from here we can find out that's the size is a function of time, and it's n, which is the size, is proportional to 2 raised to power t. In this case, t is the time, p plus 1. And if we take the reverse of that, because this is the size as a function of time, but we want to find out the time as a function of size, because that's we are interested in not in size, but we are interested in time complexity. And we can find the time as a function of size by reversing this function. And we know that the opposite of this power 2 raised to power something is the logarithmic log of 2n. So we get this as t is directly proportional to log of n. And from here we find out this time complexity for this binary search is logarithmic function of input size n. Okay. And also, in general, from there we also learn a general rule that if an algorithm solves the problem n in a fixed number of times, then its time complexity will be logarithmic. Yes, we have a question. Okay, so I thought that. Okay, yeah, okay, yeah. And here we have an implementation in Java for this binary search algorithm. So we have here we have a function with the name of recursive binary search, and it takes an integer array and an element that you want to search. And then the basic idea is that since we are using it recursively, so we find the starting index, which should be minimum position 0, and then we need to find out the size, which is we can get it from array length minus 1, and then we call this binary search method or the function, and in this function we pass the array, the element, and the part of the array that we want to search on. Okay, and so basically this min max, these are pointing to these your intervals. So should I look into the left half or the right half? And if you find it, this condition says that if the max becomes greater than the minimum value, if the minimum becomes greater than the maximum value, it means that you have checked all the elements, but you have not found the value, so it should return false in this case. Otherwise, you take the middle position, and then you check if the middle position is equal to the value that you are looking for, and then in that case you have found the element, so you should return true. Otherwise, you keep on dividing it into 2 halves until you get an element. So so far we have looked about these 2 search algorithms, linear search and binary search. What about hashing and binary search tree? So you have already searched these data structures, so hash tables and binary search trees. So what will be the time complexity if you have a data in the form of a hash table? How long time you will take to find a value in a hash table? Yes? Sorry? Constant. And if something is a constant time, then the time complexity is expressed as O of n. Yeah. Okay, big O of n. Yes, both of you are right, because in the hash table, if you remember that I mean to store, but there is also this requirement. Okay, And this requirement is that we assume that your hash table is a kind of a that comes with a perfect hash function which divides the value evenly among all the buckets. So, and it means that the number of buckets should be more than or equal to at least the number of elements, and the elements are evenly distributed. So we compute the hash value, yeah, we identify the bucket, and if you have a, and then because you can have a linked hash set as well, and it means that at every bucket you have a linked list. But if you have evenly distributed elements, usually this list will be very short, only one element at every bucket. So in that case, you have a fixed number of computations. So O of n will be, yeah, O1. Okay. And what about binary search trees? What will be the time complexity of a binary search tree? If you remember in the data structures, we learned about binary search tree as well. So where we have a root element, and the values which are lower than the root element are on the left subtree. It's like a binary search tree. Okay. And if it's like a binary search tree, then its time complexity is also same like a binary search algorithm. So it will be again a logarithmic. Because in the binary search tree, we will be dividing into the halves and looking at the values in the halves. And then we have another, coming back to this sorting algorithm. We already looked at two sorting algorithms. One was insertion sort, another was selection sort. Both have a time complexity of n square. And however, we have another algorithm, merge sort, and the basic idea behind this is divide and conquer approach. So what we do is, if you have a list, we divide the list into two halves, and we keep on dividing until we go to the list of size 1. And 1 we have hit the lowest level, because you cannot divide below 1, and then you stop, and then you start merging them. And while you are merging, you merge them in the right order. Okay, so we have divided them, and after dividing them, we combine them. And when we combine them, we put them in the right place. Okay, so that's the merge sort. So we divide recursively the unsorted list into two sublists until we get one element, and we then merge them until we get the whole elements. And about the time complexity of this array, any idea? Sorry, this algorithm. What will be the time complexity of this? How many levels are there? If you think about in terms of size, what is the size here? 1, 2, 3, 4, 5, 6, 7. So if the size is 7, how many times it takes to go to this divide and merge? 1, 2, 3 for the divide. Okay, and so if you compare 3 in terms of size, so 2 raised to power 3 is 8. So approximately, it becomes logarithmic. And then for each, I mean, we have to work in each level to combine them. So it means that we get this smallest parts equal to the size of the list, and the size of list is n. So it means that if we have 100 elements, we have to combine 100 elements, and if we have just 10 elements, we have to combine or the merge 10 elements. So basically, we have two parts here. We have this log 2n for the divide, and then and also the merge, and then we have for each merging we have n elements. So if we have we have to merge n of them. So in that case, the time complexity will become O of n multiplied by logarithmic. So we have some computations to divide, and we have some computations to merge them. Okay, so and in this case, so this is faster than the linear and selection. Sorry, merge and no, I'm confused. Insertion sort and selection sort, because it takes lesser time. And here is some outline about the merge sort algorithm. So you have a method with the merge set, and it takes an integer array and return the sorted list. So if array is of size 1, so you can send that array back because you cannot divide it any longer. But otherwise, you divide array into 2 halves. We can say that 2 halves either as left and right half. And on each half, you call again this same method recursively, and left and right, and keep on until make calls on that, and the returned arrays left and right are no sorted arrays, because this returns when it goes to the 1, it will return. And then once you have done this, you can combine the left and right part to get the sorted array, and then later on you return the sorted array. Okay. So that was something about time complexity and algorithms. So that brings us to the end of today's lecture. And the next time, on next Tuesday, we will talk about formal languages and concepts from the finite automata and context-free grammar. So there's more about formal language concepts. Okay. Okay. So thank you for today, and we see you in the next lecture. Goodbye.